Good morning, physics. Today I'm going to tell you a little bit about torque and specifically how to deal with multiple torques because you guys already have some background on torque. And so I'm going to try to, reinforce that and review that, but then I'm also going to hopefully help you guys understand how to deal with having to calculate more than one torque at once. So our general approach today then will be to first review what it is that we already know and learned about torque, and then to expand upon that knowledge. So the first thing we want to reinforce here is that torque is equal to RF times the sine of theta. Okay, and what does this mean exactly? Well, first of all, when we say a torque, we mean a force that causes a rotation. Okay, so a force that causes a rotation, that's what a torque is. Okay, and what we know about that is that there's some distance r for that force, and that distance r acts as kind of our leverage for creating this torque. F, of course, is the force that we've always known and we've been dealing with, and then there is an angle theta as well. And the angle theta is the angle between, it's the angle between we'll just say R and F, the force and the distance, okay? So the units here, just to remind you, a torque has units of Newton meters. R is measured in distance, which is meters, and force is newtons. And then, of course, theta can be degrees is fine, as long as your calculator is in degrees when you calculate it. So, yeah, so that's what we know about torque. You guys had an assignment on this already. So, what I want to introduce to you guys today is how to deal with a situation where there's maybe more than one torque. Okay, so you might have an object. In fact, we might have something such as a door. Okay, so a door, and the door has a couple of hinges over here. Okay, so there's your doorknob. And you might have a situation where two people are pushing or pulling on a door at the same time. So what we're going to do is we're going to change our perspective on the door. We're actually going to look at the door from above. So your eyes are going to be up here. This is weird, right? You're not used to having your eyes above the door. But if you were to look above the door, then what you're going to see is a rectangle that looks like this. And the hinges are going to be over here with the doorknob right here. And from that perspective, we can understand how a force causes a rotation on a door more easily. So, for example, if you're going to pull on the door, then you might exert a force in this way on the doorknob, and that's going to cause the door to, of course, swing open like that. Okay? But we're going to use this example to try to understand how your force creates a torque, and how multiple forces create multiple torques and affect the motion of the door. So, for example, you might pull on a, let's say you're going to get into kind of a pushing match on this door. You're going to try to push this door inward. In fact, you're not even going to use the doorknob. You're going to push inward with your shoulder, okay? And then another person's going to come over here and they're going to push this way. And so you're trying to cause the door, this is your force, we'll call it F1. And there's another force over here, we'll call it F2. So let's say F1 is trying to cause the door to rotate counterclockwise. And then the other force F2 is trying to cause this clockwise rotation, right? So, generally, we choose counterclockwise to be positive, just so you know. It's just a convention, but it doesn't really have to be. But it's very important to understand that these two forces will create opposite torques, and since one of those torques is opposite the other, then we have to have positives and negatives. So generally we choose counterclockwise to be positives. It's just convention, but to be fair, when you solve a problem, you can choose whichever coordinate system you wish. Now there's going to be an R associated with each force. So here we can call this R1, and here we can call this R2, okay? And so we then have these two forces creating these two torques, and the question is, okay, well, which force would win? And, how do we figure out how the door moves? How do we deal with, these multiple torques? And so the general idea is if we had a situation where in Newton's laws, say we had some box and we had two forces that were competing with each other, what we would do is we would just, subtract the forces, and then we'd set them equal to mass times acceleration. So we're going back to what we're familiar with for just a moment. Back with Newton's laws, we'd have something like F1 minus F2, and the total of these two forces would be equal to the net force, which was ma. So we had this equation in our minds, F net equals ma, and what we did then was we found the sum of those two forces, that was F net, and then we added those two together and we set that equal to ma. And so that's how we would deal with it if we had just net force and two forces acting on an object, no rotation, just acceleration. Ooh, wrong thing. I was trying to do this. So how is it that we are going to deal with it when we're not just trying to create a linear acceleration? How do we deal with it when we're trying to produce an angular acceleration? In the case of the door, we are trying to cause it to rotate. So how are we going to deal with that situation? Well, here's what we're going to do. We're going to have not two forces, but we're going to have two torques. And if we add two torques together, then we have what we call the net torque. And you may recall when we first introduced this unit, we introduced some terms, things like, angular displacement, angular velocity, angular acceleration, and torque. And then we also introduced a term for mass. So instead of F net equals ma, we have torque net equals, and instead of mass, we have I. So we're going to have I for inertia, and then acceleration will be angular acceleration. So we have two new terms that we've seen before, at least briefly, and that is the net torque is equal to the inertia of the object times the angular acceleration of the object. So for the door, we're going to have these two torques to produce the net torque, and then the door has some inertia, that is, it has a mass and it has an orientation for its mass, or a distribution of mass, which we'll talk about, and it has therefore some sort of angular acceleration. So the way an object responds to a torque will depend upon its inertia. So this is, again, very similar to the concept of net force. So a big heavy door will open more slowly than a light door. Or a door that's pushed on really firmly with a large torque will open more rapidly than a door that is just pushed on lightly. So that's what this equation says. Net torque equals inertia times angular acceleration. So how is it that we calculate our net torque here? Well, just like we would write a net force equation as the sum of forces, we can write a net torque equation as a sum of torques. So we know that R1 and F1 are going to produce a torque that we'll call torque 1, and we know those are counterclockwise, so therefore that's going to be positive out in front, but we're just going to leave that positive sign hidden there. And then F2 and R2, well, those two together will create a torque, and we'll call that torque 2, and let me fix that 2 there. And that second torque is in fact a negative torque because it's counterclockwise, right? So it's going the opposite direction as clockwise. So therefore it creates a negative torque. And that will be equal to I alpha, as we said. So all right. So now once you've gotten to this point, you can get more specific. For example, I can calculate torque 1. I know torque 1 is equal to R1 F1 sine of theta 1. And then torque 2 would be, oh, that's a little big. Torque 2 would be R2 F2 times the sine of theta 2. And just to clean things up for a bit, we're going to move that around. There we go. And we know that's going to be equal to I alpha still. And so we've gotten more specific. We now know how to calculate both torques, and we can then go ahead and set that equal to I alpha. Now, I'll do a quick reminder here that our angle is the angle between R and F. So for this problem, it's actually easy to see that that angle right there is 90 degrees, and this angle up here is also 90 degrees. And this means that the sine of 90 degrees is 1. So basically the sine functions in this equation disappear because we're just multiplying by 1. So I'll have R1 F1 times 1 minus R2 F2 times 1 equals I alpha. Okay? And a lot of times in these problems, your goal is to try to find the angular acceleration of the door or the object. And that was the case with Newton's laws, if you remember. A lot of times what you would do is you would find the acceleration of the box as it's being pushed or something like that, right? So we're doing the same thing here. We're trying to find the angular acceleration. Before we can, though, it's worth noting that we might have to calculate an inertia. So what do we do about that inertia term? Well, I'm going to touch on inertia briefly here. And so this is going to be a quick little sidebar. But it's important to know that inertia in general is equal to c mr squared, where we'll address each term. M is just the mass. R is like the radius of the object. Okay, so sometimes that's a true radius, and other times it's not a true radius. We'll talk about that. But C is just a constant. Okay, and it's important to know that C is greater than 0, but less than or equal to 1. Okay? So the largest value C can have is 1, which means the largest formula for inertia you can have is mr squared. Every other formula for inertia is going to be less than mr squared. With that said, the important thing to understand then is that for any given shape, usually, well, at least in our class, you're just going to know what the formula for that is. You're going to look that up. You're going to, it's going to tell you that it's, for example, a cylinder, and you'll just have a reference to, oh yeah, well, a cylinder is 1/2 mr squared. So I know that, and then you calculate the inertia, and then you use it in the problem. So there are different shapes that are common, and so we'll go over a few real quick, okay? So we're going to talk about I for a cylinder. We'll talk about the inertia of a sphere. We'll talk about the inertia of a hollow sphere. So that's hollow sphere. We'll talk about the inertia of a hoop, like a hula hoop. We're going to talk about the inertia of what we call a point mass. A point mass would be something that's small and going around an object. Something like, for example, a planet going around the sun would be like a point mass. And then we're going to mention a rod, a thin rod. Okay? So what is the inertia for a thin rod? That'll be something we talk about. So with that said, we're going to just basically be given these formulas. So this is not something you have to memorize, but it's an important thing for you to know, like where it is, and you know that you have this information and you can reference it as needed. So what's the inertia of a cylinder? Well, a cylinder will have the inertia of 1/2 mr squared. Okay, so essentially what we're saying, the constant C for a cylinder is 1/2. What about for a sphere? What is the constant for a sphere? Well, for a sphere that is presumably solid, then you will have 2/5 mr squared as your constant. For a hollow sphere, it's worth noting that with a hollow sphere, you have more of your mass concentrated farther away from the axis of rotation. And the idea here is that the larger r is, the larger the inertia is. Well, what's r? R is the distance between the mass of the object and the axis of rotation. So if I have a sphere, whoopsie, I missed the center. There we go, it's close enough. So the average distance between the mass and the center of the sphere grows as the mass gets pushed to the surface of that sphere. So in other words, if I have a hollow sphere, then all the interior here is empty. And that means the inertia will be larger than for a solid sphere. So in general, as the mass of an object moves away from the axis of rotation, the inertia gets bigger. Okay? So what's the inertia for a hollow sphere? It is, oopsie, 2 over 3 mr squared, 2/3 mr squared. For a hoop, now for a hoop, you just have this, what looks like a circle. The axis of rotation would be through the center, like into the page here, and all of the mass is the same distance away from the center. It's all a distance r away from the center. So we can't get any part of the mass any farther from the center, and therefore we have a maximal inertia. And as we said, the maximum value for the constant up here, right, that maximum value is 1. So for a hoop, it's 1 mr squared, or to simplify it, we'll just write mr squared. Okay? Now what about for a point mass? Well, for a point mass, we have, again, a situation where, say, we have the sun in the center here, and we have a planet orbiting the sun out here, and that planet's going to sweep out this circle, or ellipse. Then you're going to have, again, a situation where all of the mass is concentrated as far as possible away from the center, and therefore it will, again, be a maximal inertia, which is mr squared. And finally, the inertia of a thin rod is a little bit different because a rod doesn't really have a radius. For example, I could take this rod here, and I can, whoopsie, I guess that could have worked, but I just wanted to do this, right? So if I had this rod here and I wanted to rotate it about its center, the rod doesn't have a radius per se. It really has this length here for the rod. So we're not going to be using r for the rod. For the rod, we swap that r with an L for the length. And for a thin rod about its center, this is actually pretty easy to rotate, so the inertia is pretty low. So it's got the lowest coefficient out in front of all of them instead of 1/3 or 2/3 or 2/5 or 1/2. It is actually 1/12. So for the thin rod, we have 1/12 ml squared. So really what we have here is just sort of a list of formulas that you can refer to here periodically as you need for the inertias for various common shapes. For a cylinder, a solid sphere, hollow sphere, hoop, point mass, and thin rod, you have your inertias, okay? So getting back to the topic at hand, you're going to be using these inertias to solve a problem, and what we mean is you're going to be plugging in the appropriate formula for the inertia for into your net torque equation, right? So if we come down here and paste this equation, then we are going to have, oh, that's what I need, there we go. Then we're going to have this situation of a door, and if we look at a door, let's take a look at our picture here, right? Well, that's a little complicated, so we're going to redraw it just to make it simple, right? So if we take a look at our door, we have the door here. What is this door most like? Okay, out of these shapes, obviously it's not a cylinder or a sphere, so if you think about it, it's most like the thin rod. Okay, so this is what our door's inertia is going to be approximated as. So therefore, for this door here, I will be equal to 1/12 ml squared. So then I can come in here, R1 F1 minus R2 F2, and I can plug in for I 1/12, oops, forgot the 12 there, there we go, 1/12 ml squared times alpha, okay? So at this point in a given problem, you would know, of course, the mass of the door here, you would know the length of the door, you'd be able to plug all that in. You'd know R1, F1, R2, F2, and what this means, of course, is therefore you have all the information you need in order to solve the problem. So you would essentially at this point just go ahead and calculate everything, and you'd get your angular acceleration, which would be measured in radians per second squared. And in today's assignment, once you have this angular acceleration, the problem might then ask you to use that angular acceleration in the context of a kinematic. So you'll go from doing this net torque stuff to this kinematic stuff. So you plug that acceleration in for there, and then you would go ahead and say, okay, the object starts from rest, and it goes for 5 seconds or whatever, and you would do your usual kinematic stuff that you guys already know how to do. So this is the gist of it. So to review briefly, when you have multiple torques acting on a single object, such as multiple forces on a door creating multiple torques, you're going to apply this equation right here, and that is your net torque equation, okay? So we're going to copy this real quick, and we're going to paste this at the bottom, because that's a very important equation, and we're reviewing. So we paste that, so you're going to apply torque equals I alpha, net torque equals I alpha. And then you're going to, on the left-hand side here, you're going to add up all the torques. So you have multiple torques, and each individual torque is RF sine theta, right? So you might have 2 or 3 RF sine thetas. Remember, anything counterclockwise is generally positive, anything clockwise is negative. And then you're going to go ahead and plug in your inertia. And once you've done those calculations, then the only thing left should be your angular acceleration, and you will solve for that angular acceleration. And then you might be able to use that in some kinematics. So I know this is kind of a lot of information, but really it's similar to the whole net force equals ma. You have multiple torques acting on an object, then you're going to add up those two torques. You're going to then divide by your inertia to get your angular acceleration. This is just like the idea of net force, multiple forces combining to create one linear acceleration. You divide by the mass to get that acceleration. So hopefully this made some sense, guys. I'll be available for help if you need it. Don't be shy. Come bother me. I hope you have a lovely day, and take care.